Alright, the hook has to do with this question. Is a shot putter or a sprinter more powerful? Which of course begs the question, what is power? And that's exactly where we're trying to go in the lecture today. But before, and you can go ahead and have an answer for this, and there's no great consequence one way or the other, but what's your hunch? Who is more powerful? Actually, even after we're done with the lecture, people will debate with me which is the right answer. Before we get to that, we want to talk about the conservation of energy, which is related to power, but not the same thing. And the important idea is that energy is a quantity that is conserved, that you have as much energy at the beginning as you have in the middle, as you have at the end, as long as you keep up with all of it. If there's any of the energy you stop paying attention to, then it will seem like you have less. But the most often that not keeping up with the energy happens because you are watching mechanical energy, which is rather macro energy, and there are micro energies that you are not paying attention to. In particular, heat. But chemical and electrical are also things that are happening on the atomic scale, and you might not be aware of, and they do represent energy, but you're not as aware of them as some of the other energies that are around. They are spoken of as non-mechanical energies. That would be energy. So energy is always conserved. Mechanical energy is conserved as long as some of it doesn't become non-mechanical energy. So we will do problems like this. That a stone is dropped, how fast is it moving when it has fallen? That this is a problem that would be possible for you to do in terms of dynamics. You could look at the acceleration that this stone would have, and from that you could get its speed. But it can also be done in terms of energy, and there are circumstances where it can only be done in terms of energy. Often it is easier to do problems in terms of energy. So you would start this problem by asserting that you are going to do the problem in terms of energy, and I would like to see this on your papers. And then this is very much like doing a free body, where you identify the forces, and you start by identifying the body, and then you identify the forces acting on it, and if you pick the wrong body, a free body will not work for you, and if you leave out some of the forces, a free body will not work for you. Well, again, when you're doing in terms of energy, you need to choose two energy situations, and the energy is the same at both of them, and you need to list all the energies that are present, and if you leave out any of those energies, you're going to get the wrong answer. So this stone is dropped, and that's a key word. To drop it means it was standing still when you let go of it. I'm going to take that as my first energy, and the second one is going to be at this time when it has fallen 1.5 meters. Well, when it was let go, the only kind of energy it had was gravitational potential energy, which you recall the formula for, I hope. And when it has fallen 1.5 meters, it would have both gravitational potential and kinetic energy, and that kinetic energy, of course, is going to be related to the how fast. However, I'll pull in the formulas. This h is a tricky little number. that we would like to put a 2 in for h. It's dropped from 2 meters. How fast is it moving when it's fallen 1.5? Well, in that case, if I put a 2 in for h, I need to have an mgh over here because it is still going to be up in the air by a half a meter at the end. However, you could also do the problem by, here, I'll write it in. So you really ought to have a plus mgh, because there would also be gravitational potential. And you would put a 2 in for h, and over here you would put a 0.5, because that's the height when it's fallen that far. Notice I don't need to know about the mass of the stone, even though they gave it to me, because it could divide out of all those terms. But note, it would also be possible to choose as your 0 height this place right here. After it had fallen 1.5, that is when it is 0.5 up. Well, in that case, you could put in for h 1.5. And then what you would put in for h over here would be 0. That is, there would be no gravitational energy when it is at that height. And then you would have this problem set up the way I had it set up previously. You can see algebraically that if I subtract the 0.5, mgh times 0.5, mg 0.5 times this one, I am going to get mg times 1.5. So algebraically it's going to come out the same. So not a great crisis. I'm going to use this 9.8 times 0.5. Notice that the mass I'm not including because it's divided out, and you solve this problem for v, and it should be one of these answers here. Okay, now, having watched me do that problem, I hope that you will take the reins and guide us through the next problem without any assistance from me. That stop this show and do this problem. And if you get stuck trying to mimic what was done on the previous page, then start the show again. And I'm going to do the problem, but I want you to try to do the problem. And then after you've watched me do it a little, maybe you'll stop it again. You say, I can take over now, Mr. Houghton. You just stop talking. And I will. You have complete control over my mouth. Okay, so now presumably you have resumed because you were stuck. I want this problem done in terms of energy. In fact, this time the problem can only be done in terms of energy conservation. That you could not do it in terms of forces and accelerations and all of that stuff. So please indicate that that's what you're doing. And then I need these two, the choice of what my two energy situations will be. And I'll take the moment when it was thrown, and then when it is 0.8 meters. I presume that's 0.8 meters up. And then when it is thrown, it's going to have both kinetic and potential energies. But I can't do anything with that I don't know how fast it was thrown. I know how high it was thrown from, but I don't know how fast. So it is better in this case to just say that at that moment it was thrown, the total energy was 400. They told me that. And when it is 0.8 meters up, it has both the energy of motion and the energy of being up. Note, this time I could not choose that 0.8 up to be my 0, because then I wouldn't know how much energy you started with. I presume this 400 is with the assumption that we are choosing our 0 height to be 2 meters below the place where you threw it from. All right? I I hope you're stopping me when you get can take over again, but that we would then use the formulas for kinetic energy and gravitational potential energy, and then you would substitute the values in. And you have V as your only unknown, and so it ought to be one of these here. This is a much more challenging problem, and it goes, oh, we ought to get rid of this stuff. Sorry. Don't look! Okay, so here's a much more challenging problem for you, and you see if you can do it. And I will presume that you have given up on your ability to do it because you are listening to me again. That you're going to do it in terms of energy conservation. I will take the moment when the ball is dropped to be my one situation, and when the spring has been squished by 0.4 meters will be my other situation. And so, oops, come on now. The energy, when it is dropped, is going to be just gravitational, because it's dropped, so it has no kinetic, and the spring is not squished, so it has no elastic. But when it's here, it's going to be moving. They say it's moving at 3, so it's got kinetic energy. It is still up in the air, it's got gravitational energy, and it has elastic energy because the spring has been deformed. Then you put in the formulas for those, and then you plugged in values using the height was 2, and the kinetic energy, mass and velocity squared, and the gravitational energy at the end. Notice I use 0.6 instead of the 0.4. It was important to know that this spring was 1 meter tall, so when it's squished by 0.4, it is still, you are still 0.6 up in the air. And they actually asked me for the kinetic energy, so I got a little ahead of myself putting in a formula there. I just want to know that quantity. Surely you could solve this, and that should be one of those values there. Now, we go on. The next task on your worksheet was to determine the spring's elastic constant. And go ahead, stop the show. See if you can't do that. And indeed, if you needed my help, you would take the answer that you got here and set that equal to the formula for the elastic potential energy, and surely you could solve that for K. So that's what you will put on your worksheet. And then finally, at least for this part, they ask if the ball were rested on the spring, how much would the spring be squished? And this, again, you've got an equilibrium. It's resting on the spring, not necessarily down by 0.4. That is, it does not, the ball is in equilibrium. The weight of the ball and the force of the spring are equal, and that's exactly the approach that you would take, that the force that the spring pushes upwards is equal to the force that the ball pushes down. Those two forces adding to 0, we've got equilibrium. Here's the formula for the force that the spring. Notice I leave the minus off because all the minus is about is the fact that it's a restoring force. That is, that the force is in the opposite direction to the deformation. But what I want is that the magnitude of the force in the spring is equal to the magnitude of the weight. And you have the value of K from this problem here. So X is your only unknown, and you fill that in. You have this rather long problem to read through that I got 2 people putting chairs up on top of a table. One person is very facile with it, and the other person has to struggle, the 3-year-old. So, or we have this old car and a spiffy race car, and they both, instead of putting chairs up on a table, they both speed themselves up to 60 miles per hour. what's the difference? They both are doing the same amount of work, the 3-year-old and me, the old car and the new car. Same amount of energy is being transformed. So what's the difference? And the difference is how quickly you can do it. I am more powerful than a 3-year-old. The spiffy car is more powerful than the old wimpy car. That power is the rate of working, that is, work divided by time, or energy transformed per time. The units of power would then be joules per second, but a joule per second is renamed a watt. Probably should have been a lowercase w, because we're talking about the unit and not the fella. When it is, the symbol for it is a W, which is just like the W we use for work, and it's just like the W we use for weight. And so you are going to have to determine from context whether the W means work, weight, or watts. What a fun challenge. Finally, in the unique instance that the force is constant, we take that power is work per time, but work, when you have constant force, is the force dotted with the distance moved per time, but distance per time is velocity, and so force dot velocity is also a way to calculate power, but only in the instance when the force and the velocity are constant. Thank you. Have a good evening.